Welcome back. In this video, what I want to do here is move away from Boyles Law, which you may recall involved changing volumes and temperatures, assuming that pressure remained constant. We also talked about the Kelvin temperature scale and the need to add 273 to degrees Celsius to get our temperature in kelvins. Well, in this video, we're not going to use the Kelvin scale at all because we're going to keep temperature constant. And what I want to do is describe the relationship between pressure and volume for gases at constant temperature. There are many examples of this relationship, which is known as Boyle's Law. And one of the best examples would be a piston or a syringe of some sort. So I just happen to have my old-fashioned fire extinguisher here that has a piston, and of course, in order to pressurize this, one would pump it up and down and allow that to become pressurized. So when I open up the piston and move it up, there's a greater volume of gas here, which is under a lower amount of pressure, as you might imagine. As I push down on this piston, it gets harder and harder and harder to push. And of course, we're compressing until I get it really down. We're compressing all of the molecules into the bottom of this container. So it works very much like a regular syringe would look like in a healthcare setting. So that's really the gist of Boyle's Law. If you think about it, if we have a large volume and we have a low pressure, that can be altered quickly by declining the volume, and what's left is an increase in pressure because the molecules, as they get compressed, get closer together. And that is really all we need to know as far as Boyle's Law goes. So let's look at Boyle's Law. This is in section 11.9 of our textbook. Well, I've drawn a couple graphs here that kind of outline what we're talking about. It makes sense that pressure and volume kind of work opposite with one another. As one goes up, the other goes down. And as the other one goes up, the other one goes down. So it's not a direct relationship. So as pressure goes down, volume goes up. And as volume goes down, pressure goes up. Well, mathematicians and chemists and physicists all want to get straight lines from curved graphs. And it just turns out that if we plot the inverse of pressure, 1 over P, as a function of volume, we get a nice straight line. Well, that tells us that volume is proportional to 1 over pressure. In other words, P times V is always a constant. If you think about it, that makes sense. If we have a very high volume or large volume here, we have a very low pressure. So one goes up, one goes down. As we compress, we know our volume is much smaller, but our pressure is much larger. When you multiply P and V together, at any of those points, it always ends up being constant, assuming the temperature remains constant. So, that is Boyle's Law. In a nutshell, the mathematical relationship is P1 V1 equals P2 V2. The definition of Boyle's Law is simple. For a fixed mass of a gas, of an ideal gas, and that just simply says that the mass of the gas in this sealed container cannot get in or out. It's locked in. So it's fixed in place. So for a fixed mass of an ideal gas, at constant temperature, the volume varies inversely with the pressure. Now, let's look at an example. The example that we're going to go through involves a piston. So if we have 3/4 of a liter in terms of the size of a piston, and it's full of oxygen, and it's trapped at 1 atmosphere of pressure, which you'll remember is 101.3 kilopascals in a cylinder. If we move that piston and make it smaller, make the volume smaller from 0.75 to 0.5, we know that the pressure has to go up, because as one goes up, the other goes down. The question is, find the final pressure if the temperature of that piston remains constant. Let's write down what we know. We know the initial pressure is 101.3 kilopascals. We know our initial volume is 0.75 liters, or 750 milliliters. P2, the final pressure, is unknown, so we're going to call that X. V2, our final volume, is half a liter, or 500 mils. And I drew some pictures to show you the piston initially at 3/4 of a liter, and the cylinder is a little bit bigger, and when you push the piston down, the volume drops, and of course the pressure is probably going to go up. Let's do the math. P1V1 equals P2V2. Let's solve for P2, that's our unknown. So V2 goes to the bottom on the left-hand side. P1V1 over V2 equals P2. And when we plug in our numbers, we get 101.3 kilopascals times 0.75 liters, all divided by half a liter. And look at this, my friends. We get an answer that makes sense, about 150 kilopascals, or 1.5 times 10 to the 2 kilopascals. Does it make sense? Well, you can see that our volume has gone down by a third, roughly, from 3/4 to half. And one would argue that 150 is about a third times, one and a third times the size of 101.3. So I am going to bank on this question being correct. And that's all there is to Boyle's Law. I hope this helped. We will look at another gas law in the near future.